In this video, we introduce state variables in state space models. A state space model rewrites the dynamics as a system of first-order ordinary differential equations. The key idea is that we introduce state variables. State variables are dependent variables, usually functions of time. They are chosen so that every differential equation in the model is first order. So, for now, the most practical way to think about a state space model is this. It rewrites the dynamics as a system of first-order ODEs using state variables. In state space, we collect the state variables into a vector. We usually write this vector as bold X. For example, bold X may contain x1, x2, and so on, up to xn. The general state space form is x dot equals f of x. This means that the derivative of the state vector is given by a function of the current state. In other words, the model tells us how the current state determines how the state changes over time. This is the basic shape of a state space model. A useful rule is that the number of states equals the total order of the ODEs. For example, if we have one third-order ODE, then we need 3 state variables. If we have 2 second-order ODEs, then the total order is 2 plus 2, so we need 4 state variables. If we have 1 second-order ODE and 1 third-order ODE, then the total order is 2 plus 3, so we need 5 state variables. The reason is that state space form rewrites the dynamics as first-order equations. Higher-order derivatives are handled by introducing state variables, so that the final model contains only first-order ODEs. In practice, this means that once we choose the state variables, we will end up with one first-order ODE for each state. Now, let's look at how we choose state variables. For example, we might have the second-order ODE q double dot plus cq dot plus kq equals 0. Because this ODE is second order, we need 2 state variables. A standard choice is x1 equals q and x2 equals q dot. Next, we look at the derivatives of these state variables. Since x1 equals q, we have x1 dot equals q dot. But q dot is x2, so x1 dot equals x2. For the second state, since x2 equals q dot, we have x2 dot equals q double dot. This is the key point. The second derivative, q double dot, is not a third state. It is the derivative of the second state. The original ODE then tells us what q double dot is. Rearranging the ODE gives q double dot equals minus cq dot minus kq. Then we replace q dot with x2 and q with x1. So x2 dot equals minus cx2 minus kx1. Now, we have 2 first-order equations. One equation for x1 and one equation for x2. State names are a convention. The 2 common choices are to start counting from 1 using x1, x2, and so on, or to start counting from 0 using x0, x1, and so on. Both conventions are fine, as long as the state variables are defined clearly and used consistently. Other labels could also be used, such as alpha and beta, or even unconventional labels like x73 and x42. Those labels are not wrong, they are just harder to follow. The order of the states is also a convention. This means the order in which the variables appear in the state vector. Changing the names or the order can make the equations look different, even when the underlying system is the same. This is why conventional notation is useful. When learning state space, it is usually best to use standard names like x1 and x2, or whatever convention your subject uses, and to put the states in a sensible order. The key point is this: the names are labels, but the definitions matter. A common shorthand appears in many textbooks and worked examples. After defining x1 equals q and x2 equals q dot, the state vector is sometimes written as x equals q dot. This is the same state vector written using the state definitions. This notation is not wrong, but it can be confusing when you are learning state space. The second entry, q dot, is not an instruction to differentiate q inside the state vector. It is shorthand for the second state variable x2. So this notation only makes sense after the state variables have been clearly defined. Now we can explain why the shorthand still works. After defining x1 equals q and x2 equals q dot, the state vector can be written as x equals x1 x2, or using shorthand as x equals q dot. But the state vector x contains variables. It does not contain instructions to differentiate. The derivatives of the state variables appear in x dot. So even if one state was originally defined using q dot, that state is treated as an undifferentiated variable inside x. A physical example is velocity. If v equals q dot, then v is a variable in its own right, and its derivative is v dot equals q double dot. In the same way, if x2 equals q dot, then x2 is the second state variable, and its derivative is x2 dot equals q double dot. That derivative appears in the vector x dot, not inside the vector x. This is why the shorthand x equals q dot does not break the idea that state space models are systems of first order ODEs. The model is still first order because the equations describe x1 dot and x2 dot as functions of the state variables. In short, x stores the variables and x dot describes how those variables change. The general state space form is x dot equals f of x. This means that the derivative of the state space vector is given by a function of the current state. If that function is linear, then it can be written as a matrix multiplied by a state vector. So in the linear case, we can write x dot equals f of x equals ax. For the example in this video, the state space model is x dot equals x2 and minus kx1 minus cx2. This can also be written using the matrix A, where A has first row 0, 1 and second row minus k minus c. This matrix form gives us the same state space model. The key point is that x dot equals ax is not the definition of state space. It is the linear special case of the more general form x dot equals f of x. A state space model does not have to be written with a matrix, but when the model is linear, it is convenient to write it in matrix form.